Okay, so welcome back. This is part 2 in our series where we're going to help you to understand a device that is extremely common, used all over the world by many or most industries. And in fact, you've probably got a simplified version of one of these devices in your home or office. And the device we're looking at is called a relay. And I encourage you to look at the previous video in the series where we talk about the concepts, what it is, how it works. And it is very similar to another device that you might have in your home or office and is used virtually everywhere in the real world, and that's called a fuse. And I also have a video on what are fuses. I encourage you to take a look at that. Really important that you understand these devices since they're used virtually everywhere. So what we're going to do is we're going to build this, what you see here, a simulator to simulate a real-world commercial overcurrent relay. And again, I encourage you to look at the first video to explain what all that is. But this simulator we're going to build here has some very simple functionality. What I'm going to do is I'm going to open a connection and start the simulator. And you can see here that basically what this is doing is this is taking in some current. And it is displaying it here. And as we talked about before, the basic function of this relay, and we're modeling an overcurrent relay, is to take in some current from a circuit, measure it, and determine if that magnitude of current is above a value that is set by the user. And you can see down here we have set 2 amps of what's called the minimum trip. And if it exceeds 2 amps, this relay has an internal timer, and we'll start timing and say, hey, if that overcurrent greater than 2 amps is existing after that time delay, I'm going to go and I am going to send a signal out. And generally what it's going to do is it's going to do what you see here. We've got a circuit breaker that is normally closed, and if the current exceeds the value for a certain amount of time, it's going to send a signal to open the breaker, disconnect the circuit so that whatever is causing that overcurrent goes away. So that's the basic functionality we're going to model in this application. Now you might think, where are we getting this current from? This is a software simulator on our computer, but where's this current coming from that we're measuring? Well, here is kind of a overview of what I've got set up on my bench. And we're starting with this DC power supply. And when I turn it on, it's going to feed a little over 5 amps. And that 5 amps is going to go into this current sensor. And I did a video on this low-priced, very useful current sensor. And basically what it does is it can accept 0 to 10 or even up to 30 amps with the right model. And it will give you a proportional voltage output. And it will be between 0 and 5 volts, proportional to the 0 to 10 or 0 to 30 input current. And we're feeding that 0 to 5 volts into an Arduino. And the reason we're doing that is because it can take that value and send it over a COM port, a USB COM port, to our computer. So it's taking 0 to 5 in, and as we've talked about before with the Arduino, converts that voltage into a value from 0 to 1023, proportional to that 0 to 5 volts. And what we're doing is we are setting up with our software simulator that we're going to be developing. We are sending a request to the Arduino every half a second or tenth of a second saying, hey, what's the measured input voltage proportional to this current? And it's going to send us the 0 to 1023 value. So our simulator that we're building has got to take in that 0 to 1023 value, convert it back to current that's coming from the power supply. So we're going to have to do some conversion based on these devices, how they respond. And it's going to convert that back to amps. And it's going to feed it into this relay logic that we're going to develop. And like we said, if the current gets above a certain value that the user sets, the relay logic is going to say, hey, the current is exceeding the value, I'm starting a timer. And if the current is still there after the timer times out, it's going to send a signal out to trip the breaker or whatever. So on our bench, we're going to have this set up with a sensor, an Arduino, and a DC power supply. But ultimately, we just have to get these 0 to 1023 values, convert them to amps, and then apply them to the relay logic that we're going to set up. So here is our device. And what I'm going to do, I am now connected to our Arduino, and you can see it's measuring around 0 volts. It's bouncing around, but I've got the COM port open and I've got the simulator running, and here I've got some parameters that we can set. And we talked in the previous video about the curve type. Basically, it defines the time current curve of this relay. So for a given amount of current, how long it will take to operate. And there are 3 types of curves we can specify. And then the minimum trip, which is the minimum amount of current that's going to be considered to be a fault. And then time dial is another parameter, how quickly this thing will time out. And here we've got 2 lights. And I'm doing another video showing how we do this in software using a picture box. But presently, with no overcurrent, the circuit breaker is closed. What I'm going to do is I'm going to turn on the power supply, and you can see the current's going to go up. And after a certain time delay, as determined by these settings over here, it's going to open the breaker. So I've just applied 5.6 amps, and you can see it's reading that on the output. And the time delay is counting down to 1, and it has tripped and has opened the circuit breaker, and it took 10 seconds based on these settings. And that's basically how an overcurrent relay works. So we're going to show in this video how to implement most of this functionality, and that will hopefully help you understand in much more detail how these relays work. So here I am in my solution, and this is a C# Windows Forms application, and we're using Visual Studio. And if you haven't done software development before, I encourage you to look at my 3-part series for beginners, where we show you how to do the basics of writing a C# software in Visual Studio. Again, Visual Studio is free. What we've got here is the primary component of our application, and that is a class that I've called overcurrent relay. Now, to add a class, you go up to your project, right-click, add, new item, and select class, and you will get a new class. I'm defining it as public and calling it overcurrent relay. And this is going to be a self-contained model or simulation of a real-world relay. And as you can see here, I've got properties, I've got a constructor, methods, and event handlers. Now, I'm not using any event handlers. I've got it all commented out. The way this is working is we've got our main form, and that's going to have a timer, a system simulation timer. So every time step, it's going to call a method in this overcurrent relay and say to the overcurrent relay, hey, check the current that's coming in from our bench equipment. Check it against whatever setting you have for a minimum current, called a minimum trip current. And if that incoming current is greater than the minimum trip, start your own timer internal to your code. And if the current is still there after the timer is timed out, then do something. In our case, we're changing some status lights. So really, it's pretty straightforward. The important thing is this overcurrent relay has all of the properties and methods and everything it needs to do its work. So it's a great way to actually simulate a real-world device that has properties and methods and functionality. Now, it's got a bunch of properties. And first of all, we've got an ID. You don't need that, but presuming we might have multiple relays, each one can be assigned an ID. So I've got a public integer ID. And then we've got 5 status indicators, because we're going to want to know what's the status of the relay. Is the fault detector picked up? That's a Boolean, so that's a property. Is the timer running? That's a Boolean. Is the timer timed out? Is the relay tripped? What is the time current characteristic time? So basically, it takes in a current value that's over the minimum trip and checks internally what's the time that the time current curve says that the timer should go for. Next, I've got a trip timer seconds, which keeps track of the number of seconds the trip timer has been running since the fault's inception. So you can do the countdown. Trip time remaining, which is how much is left before it's going to trip. MTPOW, that is, as we saw in the previous video, there is a time current characteristic equation that defines for each current how long it should take to operate. And this is just one of the portions of the equation that define that. And we'll talk about that later. And then I've got two lists of doubles that are going to maintain the time and current values if it is above minimum trip and the relay is timing. It's going to keep track of the time and current so that later on we can make a graph of the fault current versus time to get an idea of how the relay operated. In the real world, it's called digital fault recorder, DFR. So we're saying digital fault recorder, time and current. And then we've got some settings and characteristics for the particular relay. Pickup amps, which is a double. At what amps will it start picking up and timing? What is the time dial? This is a double that defines the time dial setting. What's the curve type? We talked about that previously. And then there's some private doubles, which are parameters defining the time current curve. So a bunch of properties that we're going to need to do our work. Then we've got a constructor. And basically the constructor takes in from the user the curve type, the time dial, the pickup amps, and an ID if you need that. And here all we're doing is we're assigning the local properties with this curve type, the time dial, and the pickup amps, and relay ID, and we're initializing the trip timer seconds to 0. We also are saying the fault detector is not picked up, it's false. The timer is not running because we haven't seen a fault yet. The timer is not timed out. And then we are instantiating the DFR time and current in new lists of doubles. And then we're calling an internal method to define the curve parameters based on the curve type and time dial that the user has specified. So we're just starting it up with the constructor, and in the methods, this is where all the work gets done. The defined curve parameters that we ran in this constructor is this method right here. And what it does is it says if the user has specified a curve type of 1, then these are the curve parameters, the A, B, and rho parameters for the curve. And that's for a moderately inverse curve in the US IEEE curve parameters. Else, if the user has specified an inverse, it's a curve type 2 with these parameters, curve A, B, and rho. If it's very inverse or curve type 3, it's these parameters, and extremely inverse curve type 4 with these parameters, and short time inverse curve type 5 with these parameters. So this is just setting up the internal curve parameters for the relay. Now, overcurrent relay is the method that gets called each time step, and this is the real workhorse of the relay. It takes the real-time current, checks the real-time current curve, and determines the corresponding time delay at that current before tripping. So what we've done is we've got called a multiple of minimum trip, which is the line amps. And what we're doing is we've got a SCADA class, which is a public static class that just is a repository for data that we're going to use in our simulation. The time seconds, the simulation time seconds starts out at 0. The time step milliseconds, the user can say, in this case, every 1/10 of a second, we're going to have a new time step to do a calculation. And we're saving the line current that it's going to be operating on in this SCADA class. And this is just kind of a repository. We can change it later. So the minimum trip is whatever the line amps is over the pickup amps, which the user specified, this pickup amps, or the minimum trip. And this MT power is part of the equation where we just take this multiple of minimum trip times the curve rho, take a math.power, and that gives you the MT power. And we talked about that equation in the previous video. I encourage you to take a look at that. So really, all this does is it has one if statement, an if else. If the multiple of minimum trip is greater than 1.5, in other words, if the current coming in is greater than 1.5 times the user specified minimum trip current, in our case, if it's like a minimum trip of 2 and a 5.6 actual current, that's going to be about a 2.5 or 3 times minimum trip, so it's going to be greater than 1.5. So that means there's a fault that we want to deal with. So here is what we do. We basically say, okay, now the fault detector is picked up. The trip timer seconds is the previous trip timer seconds, starting at 0, plus we're taking the time step in milliseconds, dividing by 1,000 to give us seconds, and converting that to double, and we are incrementing the trip timer seconds each time step. And then we are figuring out, for the current that's coming in, what is the correct time, the correct trip time based on the time current curve. And that is the equation we showed in the previous video. Basically, the time dial times this curve B value plus curve A over MT power, which we just calculated, minus 1, and that will give us the time current curve time. So we know how long it's supposed to take at that current, and then we'll say the trip time remaining is this time current time minus the actual trip timer seconds. So we're incrementing the trip timer seconds, subtracting it from the time it's supposed to take, and that's the remaining time before it's going to trip. So that's about it. It's basically figuring out, is it overcurrent? If so, is it how much time is remaining before we trip? And at this point, we are adding to our fault recorder the time, the trip timer in seconds, which is the seconds and also the DFR amps. So this we can plot later, that has, for a fault, it's got the number of seconds and the line amps each time step, and we can put that in a CSV and plot it later. And then if trip time remaining is less than or equal to 0, so it's gone through its timing, it's a fault and it's gone through its timing, then we're going to call this trip relay method. And all that does is that resets everything to 0, and we'll take a look at that. Now, this was if we have a fault. This is else. If there's no fault, we just reset the trip timer and then set the fault detector picked up to false, and we're done. So really pretty straightforward, just taking the current, checking against the equation that defines the time current curve, and determining if it's a fault or not. Now, if it was a fault, we call this trip relay. And trip relay, all it does is it says, okay, the line amps is now 0. The relay tripped is true. The timer is timed out. The fault detector is no longer picked up. The timer is no longer running, and the trip timer seconds equals 0. Now, we can also do other things with this. When the relay trips, we can have it go do something on our bench, but that gives you an idea about what you can have this do. So that's really the basic concept behind an overcurrent relay. And we can add additional functionality later on, but this gives you a good idea about how something like this would work. So now in the next video, we'll show how to bring all this together and generate this user interface and do the time step and connect to the bench devices and show you how this all works together. So if you like any of these videos, please hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.